Hey, welcome to this channel. My name is Edison. Today you're going to follow these streams with a session in where we are going to study one of them. This paper is basically to implement in some project that I am currently working. So I don't know if most of you are familiar with computer vision. Computer vision is basically the field of artificial intelligence, in where we give the ability to machines to perceive the world with our eyes. So that is very important. Right now I am working on that. But uh, into this, I am training some models, and these models have some problems. That is basically when it's too hard, the task that we want to achieve can be a little bit complicated because uh, mm, most of the time the samples are very hard to distinguish for the model. So with this, for example, right now I'm working in some model to enhance images. So as input, I have some noisy image, and as output, I have another. Okay, so the problem here is that we need some mechanisms or another model to improve a little bit more of that. So because without that mechanisms, the model is not able to get excellent results. So with that, I was searching something to apply it. One of these solutions that I found was to apply contrastive loss. Contrastive loss is basically, we're going to search this because I'm not sure. Yeah, let me share my screen. Yeah, great. So yeah, so first thing, what is contrastive loss? So yeah, here we can find many sites. Okay, so contrastive loss, from my point of view and from some lectures that I was searching and I was reading a little bit, is basically when you have one image, you use some pre-trained model to get the features or the representation of that image in different sequences. For example, I have here. I know that one of the most models to use in contrastive feature loss is BGG. Why? Because BGG having trained it with a good data set and also is a efficient model. I read in some places that are better than other current models. For example, EfficientNet, BGG is better for that. The most recommendable is BGG 19. So, with that on mind, how all of this is working. So, basically, you can see we have two different images. We have our ground truth, and also we have a synthesized or a noisy image. With that, we are going to extract different parameters, or not parameters. We are going to extract a representation of these images. These representations is going to be in different layers. So, for example, I have my model and I'm going to extract the representation for the layer 19, 20, for example. But I'm going to extract the thing that I was observing is that it is extracting, for example, 5 layer representations, and then we can compare with the other. At the same time, we're going to do that for this image and the same for the other image. So with that, we have 5 representations, 5 states of representation of the images for each image. So we can compare the loss between them. So For the first layer representation, we're going to compare the loss here and then the representation loss here and here and here and here. So this is very important because with this we can really have a metric that help us to compare our one image with other, and we can compare different kind of details. As you know, the first layers in some models are the basic layers. So here we are extracting patterns as edges, corners, maybe some characteristic parts of the images. So, but when we are going more on deep, when we are going on deep of these layers, we're going to find that we're going to find complex patterns that are interesting sometimes to compare with others. So what is this important and why we are not using another kind of metrics as, for example, accuracy or recall of a1? We're not using that because basically with this we are able to compare the image in different ways, not only to take some pixel and compare pixel with the other pixel, because sometimes these images have a variation that can affect a lot the comparison with this metric. But with contrasted love we can really measure how it's working this. So all of this that I am talking about is basically because we really need the contrastive feature loss to improve our model. So for example, we're going to read this very fast, only the abstract. Training supervised image synthesis model requires a critic to compare two images. They run through to the results. Yet this basic functionality remains an open problem. A popular line of approaches uses the L1. So here they are mentioned that they are using the L1 distance. For people that doesn't know what is the L1 distance, it is basically one way of measure one point to another. So it's basically you have 2 points in some feature space, and then you want to measure in a straightforward way what is the distance between this point and this point. It is basically that. But we're going to start something easier to understand, the contrasted loss. So we're going to search here the contrasted loss. Yes, there is this. I really like this image because in this image we can observe that we have two different images that are representing numbers, but then we are using CNNs to get a representation in some vector space, and that vector representation of the one is going to result in this point of the space, and two is going to be representing this point. So with that we can observe that we can locate that images in some place too, and with that we can measure how far or how closer they are. That is very interesting because with this gives us an idea of this idea was used in generic Siamese models. That's Siamese model. Maybe later we are going to search a little bit more about that, but it is another kind of artificial neural network architecture. Sorry. But basically, the most important is that they are using these mechanisms to get an image, use a network to get the features, and then measure the loss between these points. But what do we want? So in contrastive loss, it exists different kind of contrastive losses. One of them is that, for example, the triplet loss. Triplet loss is that point in when you are not using two images or two images, one ground truth and the other the hazy images or the noisy images. No, but in most of that problem, they are using that images to push the images or to pull, depend what is the application. So with triple losses, I want to see if this is here. But let's check this first. So, well, we're going to read this. This is for Brian Wyland. So, thank you, Brian. This was from March 3 of 2020. So, he said that contrastive laws have been used recently in a number of papers showing instead of the R results with unsupervised learning, MOCO, purely sim contrastive regularization. This is very important. We are going to focus later on that. So, all follow very similar patterns of using a CMS network with contrastive laws. When reading this paper, I found that the general idea was very straightforward, but the translation from the math to the implementation wasn't well explained. That is very interesting because most of the time happen a lot that more for people that are not mathematicians as me. So as is often the case in machine learning papers, the math isn't difficult once you got the main idea. I will attempt to clearly explain how contrastive laws works and improve and provide a complete implementation using Python and NumPy. Well, let's stop a little bit here. ¿Aló? Sí, con él. Ah, ¿en serio? Ostras. Cabo un bache es en Torre Roja, ¿cierto? Ostras, pues te lo agradezco mucho cuando, en cuanto pueda paso. Vale, súper, muchas gracias. Vale, Deu. Yeah, guys, sorry for this. It was a call. Uh, this is my first live, so it was a call because I lost my transport card, so I need to go later for that. So please remind me that. So okay, so we was talking about the contrastive loss. So yeah, I thought that the general idea was very straightforward, but the translation from the math to the implementation wasn't well explained. Okay, so as it is often case in machine learning papers, the math isn't difficult once you get the main idea. I will attempt you clear. Okay, this guy is going to explain a little bit more. Yeah, this guy issues the contrast law for Chames network. So let's check what is he saying. So before digging into the details, it will be helpful to talk about Siamese networks, also called twin networks, but it's not a widely used term. When training a Siamese network, two or more inputs are encoded and the output features are compared. This comparison can be done in a number of ways. Some of the comparison are triplet loss, pseudo-labeling with cross-entropy loss, and contrastive loss. Yeah, I only know this triple loss, so let's check later what is happening. So Asciam's networks often show two different encoding networks that share weights, but in reality, the same network is just used twice before doing back propagation. So yeah, example, let's look at an example where we want to make features out of MNIST numbers. MNIST is a data set that is basically images with numbers. It is this. Each image of an MNIST number should encode into a vector that is close to vector from images of the same class. Conversely, different numbers should encode into vectors that are far from each other. Okay, so yes. Since we have the class labels for MNIST inputs, we could use a regular network and categorical cross-entropy loss. The problem is when we don't have nicely labeled data, as is usually the case, yes, there is much more labeled data than labeled data available in the world. This is where contrastive laws come in. So, what is contrastive laws? Contrastive laws takes the output of the network for a positive sample example and calculate its distance to an example of the same class and contrast that with the distance to negative examples. Said another way, the loss is low if the positive samples are encoder similars. So if the loss is have a low value, we're going to consider positive because they have many things similar because and also they are closer. So in the representation space, if is negative, if the example is negative, the encoder is going to be farther. So that is this example. So this is positive and this is a positive sample because they have a similar representation in the space, but these have a different representation in the space. That is why they are farther. Okay. This is accomplished by taking the cosine distance of the vectors and treating the resulting distances as prediction probability from a typical categorization network. The big idea is that you can treat the distance of the positive examples in the distance of the negative samples as output probabilities and use cross entropy laws. When performing supervised categorization, the network outputs are typically run through a submatch function, then the negative likelihood loss. Let's make this more concrete. This example will have two vectors that are similar, an array of the similar ones. P1 and P2 are positive vectors. Okay. With P2 being a slightly modified version of P1. Negative is the array of the similar vectors. So yeah, we have three vectors here. Okay, so one is positive, positive 2, but that is a variation of the same of this array. So okay. So please note that I have used a pre-normalized vector. Okay, so calculating the distance. In order to measure how similar two vectors are to each other, we need a way of measuring distance. In 2 or 3 dimensions, the Euclidean distance, ordinary or straight line distance, is a great choice for measuring the distance between 2 points. However, in a large dimensional space, all points tend to be far apart by the Euclidean measures. In higher dimensions, the angle between vectors is a more effective measure. The cosine distance measure the cosine of the angle between the vectors. The cosine of identical vectors is 1 while orthogonal. Okay, I'm a little bit lost here, so wait. Okay, calculating the distance. In order to measure how similar two vectors are to each other, we need a way of measuring distances. In 2 or 3 dimensions, the Euclidean distance, ordinary straight line distance, the way that I was mentioned previously, is a great choice. It's a great choice for measuring distance between 2 points. However, in a large dimensional space, all points tend to be far apart by the Euclidean measures. In higher dimensions, the angle between the vector is a more effective measure. Okay, I got it. So if we have 2 or 3 dimensions, Euclidean distance is going to be okay. If not, if we have more high dimensional to measure, it is basically we need to measure by angles. Okay, that is cool. The cosine distance, measure the cosine of the angle between the vectors. Ah, the cosine of identical vector is 1, while orthogonal the cosine of identical vector is 1, while orthogonal and opposite vectors are 0 and as 1 respectively. More similar vectors will result in a large number. Calculating the cosine distance. Okay. The cosine distance is done by taking the dot product of the vector. When not using unit vectors, you will have either normalizing the vector or divide by the product to the normal vectors. So okay, so P1 and P2 are nearly identical, thus close to 1. So post dots. So we're using P1 dot p2. Okay, so post dot is this. So most of the negative are pretty far away, so smaller negative, non-negative. So here we have the length, how many negative sample we have. Then we are creating some. Okay, here we are creating an array with the length that we have of negative samples, and then we are going to enter in this loop with that say that for in range of the num next. So for each for all the range in num negatives, so for all the samples, we're going to iterate between this I and this I. We're going to iterate into the array, and we are going to pl dots. We're going to put the negative samples of I into that part. So it basically it is the measure. Okay, so the softmax function takes the vector of real number and forces then into a range of 0 to 1 with this with the sum of all the numbers equaling 1. One other nice property of softmax is that one the values is usually much bigger than the others. So when calculating the loss for categorical cross entropy, the first step is to take the softmax of the values. Then the negative log is labeled to category. Okay, this is interesting. Let's take the summas of a post appendix. Okay, so there. So what is he doing? So here we have a mathematical form that say that a upper say zeta. Please, if you know how to say that, because I am learning English too, so help me. Yeah, let's take the submax of a pole data pen with negative dot vector. Mega vector from the positive and negative vector comparison. And be concatenated dot neg dot exponential, non-p exponential of the vector that we can calculate, concatenate here. We're concatenating the post dot and negative dot, and then we divide each value by the sum. Okay, so we are dividing all the values that we calculate in the exponential with the sum of the exponentials. So that give us it is basically normalized. When we normalize that, we have values here, and we can say that this is near or closer, right? Our positive sample 0 is much bigger than the random ones, and all bigger than 0 is less than 1. Okay, so contrastive loss right now. Finally, we get the focus on this article called contrastive loss. So the contrastive loss is basically what is the contrastive loss? Looks suspiciously like the softmax functions. That's because it is. With the addition of the vector similarity and a temperature normalization factor, the similarity function is just the causing distance that we talked about before. The other difference is that value in the denominator are the causing distance from the positive example to the negative samples. Not very different from cross entropy loss. The intuition here is that we want our similar vectors to be as close to 1 as possible. Sin log of 1 equals 0. That's the optimal loss. We want the negative sample examples to be close to 0, since any non-zero values will reduce the value of similar vectors. So contrastive loss of the example values. Some temperature, concatenate the vectors. We concatenate the vectors again, and we are dividing by the temperature. Then we are going to put everything in exponential or logics, and then we are using the loss that is the numpy. This is from the numpy library, the logarithm of the exponential of the first index of the right divided by the sum of the exponential. So with that, we are going to get the laws. Okay, that's all there is to it. So contrastive law can be implemented as a modified version of cross entropy laws. So now we know that contrastive laws have, I don't know this until right now, that contrastive laws is like a derived function of softmax. So that is very cool. Contrastive laws like triplet and magnet laws is used to map vectors that model the similarity of input items. This mapping can support many tasks like unsupervised learning, watchful learning, and other distant metric learning tasks. I hope that this article, okay, really thanks, guy. I mean, you know a lot. But that is not the point of today. I want to see. Oh, this. I was observing this the last time. So let me connect the computer because we are losing the battery right now. So this is another full guide. This is the last one. I really promise you because we need to advance. So what is the point after this? We're going to read this article. Then we have a paper that we want to read. Yeah, and after that, maybe we are going to do some implementation. So maybe today the routine is going to be